Good afternoon, everyone. I am Mr. Ish. Thank you for joining me. We're looking here at this video titled Working with Parametric Equations. This right here is a concept which is frequently seen at the end of a pre-calculus course, or normally at the end of a Calculus 1 course as a student is entering into Calculus 2. Parametric equations are important because they have a good application about them. Before you understand what parametric equations are, it's also important to understand that you know how to work with these equations. If you think about a variable, and we'll call that variable t, this t represents a parameter, a third variable that is introduced into an existing equation, and that equation would be of the x and y form. There are two types of equation forms to be familiar with, and one of them is a rectangular equation form, the other one is a parametric equation form. The rectangular equation form is what you've been familiar with all along, equations which have the x and y variable in them and only the x and the y. Such equations would be 2x minus y is equal to 3, or you can say e to the x is equal to y. These are rectangular equation forms. You can even say y is equal to 2 sine x. You have the x and the y variable. The parametric equations are those in which you see this variable right over here. You could have equations expressed in terms of t for both x and y. T is equal to 3x, and you can have another one, t is equal to 2y minus 1. You see how in this you're expressing everything with regards to t separately with the x and the y. That right there is a good example of a parametric equation. These are rectangular equations. You have to be able to convert from one form to the other and the other form back. In this video, we're working here with the parametric equations. Right here, we're looking at equations of this form where everything is expressed with this third variable. In some instances, it is advantageous to express items or quantities with respect to this third variable to enhance the qualities and the features that you are examining, and then you have to eliminate that variable and go back to your rectangular form. So when you're working with parametric equations, for this specific video, we're going to learn the skill of eliminating the parameter, going from a parametric equation to your basic rectangular equation. We'll start here with this very first question, an easy one. If t is equal to 2x, you can eliminate the parameter by recognizing that you can substitute this right over here. When you do so, you end up having 2x is equal to y minus 1. You see, when you look over here, you've eliminated the parameter. You can eliminate the parameter by using substitution and usually elimination style of techniques. And then you can convert this into the standard y equals mx plus b form. You'll have y is equal to 2x plus 1. An additional skill to understand is graphing your representation of your rectangular equation, then also determining the direction of your curve. The direction of your curve has a practical significance. We won't learn why it's significant. We're just learning right now how to determine the direction of your curve. Then down the road you'll know how to do it when it comes time to applying all of this in terms of practical type of questions. Y equals 2x plus 1. You can do two sets of values. If x is 0, y is 1. If y is 0, x is a minus 1 over 2. When you graph it out, you're getting something which looks like this. Now we have to determine the direction of the curve, which would very well be determined by your parameter. You can do so by doing a table of values t, x and y, and you determine the direction of your curve by looking at increasing values of t. Since everything here is linear in terms of equation, you can use minus infinity to infinity domain. You can just come up with three arbitrary values, minus 1, 0 and 1, and start by plugging in here in terms of t, and you solve for x. If t is a minus 1, you know x is a minus 1 over 2. If t is a 0, x is a 0. If t is a 1, x is a 1 over 2. Now you take these x values and you plug them right over here in your rectangular equation. You solve for y. If x here is a minus half, you'll end up having minus 1 plus 1 is a 0. If x is a 0, y is a 1. If x is a 1 over 2 or half, you end up having y value here of a 2. Half times 2 is 1, 1 plus 1 is a 2. Now you can look at these in terms of the direction and the trends. As the t values are increasing, your x values are increasing and your y values are increasing. You're seeing a direction in terms of your graph to be everything in this way right here. From left to right, everything is going upwards, and that right there is your direction determined. The parameter is eliminated, the rectangular equation has been solved, and this right here represents the gist of the style of questions we're looking at here in this video. We have these two sets of parametric equations. Everything is expressed here with regards to this parameter t. We have to eliminate the parameter and arrive at a rectangular equation having only the x and the y variable. We can also graph it then. Start right over here. If ln t is equal to x, then t must be equal to e to the power of x. You can substitute this e to the power of x into that equation in place of t. 2y is equal to natural log e to the x. You know, you can look at that as this 2y is equal to ln e to the x, and then you can look at that as 2y is equal to x ln e, which goes away, y is equal to x over 2. And here's my rectangular equation form, arriving here from these parametric equations by eliminating the parameter t. And we've done that. Now if you were to graph it, we can graph it out. If x is equal to 0, you know you have an origin point. If x is equal to 2, y is equal to 1. If x is equal to minus 2, y is equal to minus 1. And we have a graph which looks like this, relatively flat, not too steep. I may not be showing it very well, but that's how it is. We can draw arrows here because we have to determine the direction of the parameter. Not that we've determined the graph, we have to determine the direction of the parameter of the equation, and we can do so again by table of values, t, x, and y. But look over here, we're looking here at a natural log, so you should be thinking values based on the domain of a natural log. You don't want to go 0 or negative values. They're outside the domain of a natural log. You can pick values such as 1 over 2, half, and 2. And put everything right over here. If t is a half, then x is a natural log of a half, and you know that's a minus 0.693. Natural log of a 0.5. If t is a 1, natural log of 1 is a 0. If t is a 2, natural log of 2, well, you can just write natural log of 2. I believe that's 0.693. Anyhow, you take these x-axis values and you put them right over here. You have minus 0.693 over 2. You don't even have to solve it out, just do that. Then you have 0 over 2, which is a 0. Then you have a natural log 2 over 2. Those are your y values. Now, the direction of your line or your graph is with regards to the increasing t values. You always look at the increasing t values to determine the direction of your parameter in terms of your graph. As these t values are increasing, you're seeing a steady increase in this direction over here. And that right there would be the direction you would have to show on your graph. The parameter has been eliminated and a rectangular equation has been derived. Now let's make things slightly more difficult and change our parameter. Our parameter is no longer t, but the parameter here is the theta. And you can see that. That right there is my new parameter, because look at this. We have equations here presented with 3 variables, x, y, and theta. You have to eliminate the parameter and arrive at a rectangular equation. When you're seeing instances like this, you should be thinking about this trigonometric identity. Sine squared theta plus cosine squared theta is equal to 1. And this would very well come into play for parametric equations, which will eventually give rise to circles and ellipses. Look what I'm doing over here. I'm going to push the 3 on this side, and I'm going to equal it to cosine theta. I've pushed the 3 over here. Do the exact same over here. Y divided by 3 is equal to sine theta. Now square everything. When you square everything, you're going to give rise to this identity. You'll have x squared over 9 is equal to cosine squared theta. Then you have y squared over 9 is equal to sine squared theta. Add these components and you'll give rise to that identity. If you did x squared over 9 plus y squared over 9, that would be equivalent to you doing cosine squared theta plus sine squared theta. But cosine squared theta plus sine squared theta is always equal to 1. You're really looking at x squared over 9 plus y squared over 9 is equal to 1. You can cross multiply that 9. You'll have x squared plus y squared is equal to 9. You're looking here at a rectangular equation which represents the equation of a circle. Radius is equal to 3. We've eliminated the parameter from these parametric equations. We've arrived at a rectangular equation which represents a circle. Radius 3. And this is exactly what we're looking at. 3, 0, 0, 3, minus 3, 0, and 0, minus 3. Now we need to know the direction of this curve. What is the direction of the curve? Well, you can do that here with these table of values, x, y, theta. When you're looking at everything over here, think of things in this form, where you have theta which is less than or equal to 2 pi, which is greater than or equal to 0, because we're looking at a circle. It would very well fall right here within that kind of a domain. Look everything over here. and come up with these values. How about this? 0, pi over 2, and pi. When theta is a 0, cosine of a 0 is a 1 times 3, you're getting a 3. When cosine is a pi over 2 of that, you're getting a 0 in terms of x. For pi, you're getting a minus 3. You're getting very much these values here, which would correspond very well to the y values you're seeing over here, 0, 3, and 0. Just by looking at that, as these thetas or your parameter is increasing, you're seeing a direction which is developing in this way, right over here in a counterclockwise. So you can draw your arrows like this. This right here, right over here, represents the direction of your circle in a counterclockwise, and we've determined that by means of the behavior we're seeing here with the increasing parametric value, how the x and the y are behaving, we get that direction. Let's look at this as our last question. When you're seeing something like this involving secants and thetas, you want to be thinking about this type of identity. Tan squared theta plus 1 is equal to secant squared theta. And in terms of what the rectangular equation will be from these parametric equations, you want to be thinking about a hyperbola. And I'll show you why. You're looking here with these coefficients being pushed over here. X over 2 is equal to secant theta. Your parameter here is theta. And you have to eliminate the parameter and arrive at a rectangular equation. Here you're looking at y over 1 is equal to tan theta, because the coefficient of this tan here is a 1. It's an imaginary 1. You don't need to show it, but we know there's a 1 over here. Square everything over here. This squaring technique is very good when you're eliminating a parameter. Look what happens. You get an x squared over 4 is equal to secant squared theta. Here you have a y squared over 1 is equal to tan squared theta. Bring the identity over here. You're seeing an x squared over 4 is equal to tan squared theta plus 1, because secant squared theta is equal to tan squared theta plus 1. You have a y squared over 1 is equal to tan squared theta. Take this 1 and push it on the other side. X squared over 4 minus 1 is equal to tan squared theta, but we know tan squared theta is also equal to this, so it's equal to y squared over 1. Look at this. X squared over 4 minus 1 is equal to tan squared theta, which is equal to y squared over 1. You can cross this out. Push the minus 1 on that side and push the y squared over 1 on this side, and you'll arrive at your rectangular equation. X squared over 4 minus y squared over 1 is equal to 1, and that looks like the rectangular equation of a hyperbola. You can look at it as this: x squared over 2 square minus y squared over 1 square is equal to 1. You have a value here of a 2, b value here of a 1. You have a horizontally directed hyperbola which has a center about the origin. I want to do a graph over here for you, but I want to erase some of this over here because you've seen this. I'll erase this and you can understand what we're doing here with regards to the graph. Look at that. We have a vertex over here. Vertices are plus and minus 2, 0. We don't need to worry about the focal points. To graph it, we already have the vertices. We don't have to be too specific in terms of our graphing depiction. We're just doing a general direction over here in terms of the rectangular graph we have, the hyperbolic graph. We have vertices plus and minus 2, 0. It'll be like this. We're not going to be drawing the arrows because we have to determine the direction. Asymptotes would very likely be over here. But how can you determine the direction? You can do again a table of theta, x and y. Sometimes you don't even have to go into y. Just the theta and the x in terms of the direction is all you need. You can look at everything here in terms of values. How about we just come up with 0, pi and 2 pi, because here we're looking at angles. We'll do everything here with regards to this. If theta were a 0, we're looking at a secant of a 0, which is a 1. 1 times 2 is a 2. If theta is a pi, you know cosine pi is a minus 1. Therefore secant will also be a minus 1. In terms of that, pi times 2, you'll have a minus 2. 2 pi, cosine of 2 pi is 360 degrees. Cosine, which is a 1. Secant is also 1. 1 times 2 is a 2. You don't even need to go in here into the y. You're getting a very good sense of direction. As the angles are increasing from 0 to 2 pi, you're seeing a general direction of x-axis turn over here. You're going here from positive x-axis values. Here's my x-axis. You're going in this direction as you're seeing, and then you loop back over here. Therefore, the direction of your graph in terms of the hyperbolic curve would be exactly as I'm showing you. And since you have a good symmetry of this hyperbola, around the y-axis you have a certain mirror image symmetry, the direction will be mirrored on the other side exactly as you see it. So you see the direction of your parameter will be here, your graph in that direction. Now there's a practical significance to this direction. We'll worry about that down the road when we get to that point. Here we're only learning how to work with parametric equations, and as a bonus we're doing these graphs and determining the directions, but this is how you determine the direction. Everything here is with always increasing value of your parameter, which is usually a t or it can be a theta. And in this video, as you saw, we worked with parametric equations where we started here with two parametric equations. We eliminated the parameter. The parameter here was theta. In the previous questions, it was theta and t. We eliminate the parameter and we arrive at our rectangular equation form. From there, we do our graph. Here, it happened to be hyperbola, and then we determine the direction of that curve. And that's about all I wanted to talk about in this specific video. That right here is the focus. But you see how here we eliminated the parameter to go to a rectangular equation. There are instances where you go from a rectangular equation to your parametric equation, so you have to learn how to work both directions. Here we've only gone in this direction. In another video we can learn how to go backwards. Once you know how to work with these parametric equations, then you can start doing more with them, because there's usually a certain quality which this third variable, the parameter, brings into this entire scheme over here. Extra variable, extra information, all of that, extra things you can do with it. But the focus here was just learn how to work with parametric equations from the direction of your parameter to your rectangular equation. Hopefully you enjoyed this video. Thank you for watching. You all have a good day. Bye.